Good.
All right. Okay, so the last chapter is the one where we're talking about community ecology, and community ecology is sort of the biggest of the big picture kinds of things. And I think you'll recognize some of the themes. So when it comes to chapter 20, we're dealing with community ecology. So, community ecology. Well, first of all, we have to identify what the community is, and I mentioned to you before that this is where that huge jump in complexity occurs when we're looking at the different levels of ecology. And so, the first part of this is to simply figure out how do we actually measure biodiversity. So, measuring biodiversity is a key aspect of community ecology. Now, what does that mean? Well, it means simply how many species are there, so you can count the number of species. And then when it comes to the species numbers, you can also determine their relative abundance. Thus, we don't just look at the straight number of species, but we also want to find out how many of each there are. But it also includes what the genetic diversity is. Genetic in a group of species. If you have species that basically have very little genetic diversity, that means they can't respond well to environmental changes, and as a consequence, they may not do particularly well as a member of a community. Cheetahs are a good example. Cheetahs are so genetically limited that they're probably going to face extinction even if we didn't have human interactions. And then there's also habitat diversity. So when you have a group of organisms that live in one type of habitat, that's clearly less diverse and more limiting than if you had a group of organisms that lived in multiple types of habitat. Now, if we can measure biodiversity, we can determine how biodiversity is changing. And in most cases nowadays, we're having to document the loss of biodiversity. And the loss of biodiversity is caused by a variety of things, some of which are pretty straightforward. I mean, if you put in a mall, then you're going to lose habitat. There's no question about that. But some of them are not quite so obvious. So the first one, when it just comes to habitat destruction, that's pretty obvious. The one that's not so obvious is fragmentation. So if you're a desert tortoise and you're wondering whether you have a large habitat or a small habitat, the presence of something like I-15 or Bear Valley Road can be a very significant aspect of that. And so if you have roads or other types of corridors that bisect or dissect a habitat, then the habitat can become fragmented and you have smaller batches of habitat. We also find that there is overexploitation. Overexploitation simply means you take too many individuals out of the habitat, and as a consequence this has a negative impact on the community. You can introduce exotics, and this is not just large organisms, this is also smaller organisms. I mean, think about how does Zika virus get around? It's small organisms, right? But somehow they still can have a significant impact. So exotics are very important in that regard. And then of course there is pollution of various types. And in pollution, I also want to include something called the ecological footprint. When it comes to habitat used by humans especially, we sometimes have footprints that are much larger than our needs. I mean, think about this for a minute. If you actually were to determine your needs, not minimal needs, but comfortable needs in terms of house area, I think most people would probably be fine if, let's say, everybody had a bedroom, and there's kitchen, dining, living, etc., etc. And if you put that into perspective of the areas in each room that you actually need, you could probably live comfortably on 1,500 square feet. Now that's not a big house. That's not a teeny tiny house either. That's simply looking at some comfortable limitations for normal humans. And so then the question is, where does that leave houses that are 3,000, 4,000, 5,000 square feet big? Well, it simply means that the ecological footprint of the individuals living in those homes is significantly larger than what their needs are. Now, this is not supposed to be a value statement. I think that sometimes the big house is a nice thing. You have a pool and all that kind of stuff. But from an ecological perspective, it's clearly a greater use than would be absolutely necessary. And humans tend to be the only organisms that do that. Now, when it comes to the loss of biodiversity, when it comes to the exotics in particular, there are some examples I give. So there's the brown tree snake, that's one. The zebra mussel is another. And so there's a variety of examples in that lecture that you can look at. Now, sometimes the loss of biodiversity is natural. Habitat destruction is something that can occur naturally. We talked about some of the disturbances, these cyclical or seasonal versus the non-seasonal disturbances, things like landslides and earthquakes and so on. And they can sometimes lead to significant habitat destruction. Well, how does the habitat respond? It goes through something called succession. So succession is an ecological concept where you find that you start from scratch again. Sometimes not entirely from scratch, but sometimes from scratch nonetheless. And so we differentiate between primary and secondary succession. So primary succession means that the entire habitat is completely raised. And so you raised with a Z, not elevated, but raised, all gone. And so that kind of thing can happen clearly with earthquakes, with landslides, and so on. It can happen when you have volcanic eruptions, and they basically cover everything with a pyroclastic flow. Then you have to start from scratch. So glaciers, as the glaciers are receding all across the world right now, we're seeing a lot of this primary succession, where for millennia there really was not anything growing. Now there's space again. So that's when you start from scratch. Secondary succession means that there's still something left. So if you cut down parts of a forest, even if you clear cut it, you would expect that some of the root materials are going to be left, some of the lower canopy plant, the lower plants and the understory are left, and so from that you can actually regrow a forest. Now if you go to tropical forests in Southeast Asia, if you clear cut one of those forests and then just let it grow, it takes about 80 years or so until it grows back to a point where it's very difficult to distinguish secondary from primary forest. Primary forest is one that's never been cut, that's been existing for sometimes millions of years unchanged. The only thing that changes is the diversity in that forest. So you'll find fewer species of trees, fewer species of animals, because everything was pretty much cut down to the roots and then it had to regrow. And then one of the things that also happens is chemical cycling. And chemical cycling is something that, of course, provides reservoirs for some of the things that we need, especially when it comes to nutrients. And so we find that there are a variety of reservoirs, including abiotic reservoirs. When organisms need phosphate or sulfur, they get it from their environment. And so this is one of the things where certain minerals are definitely needed. Now, once we understand some of the basic things for how the biodiversity in a community is put together, then we can look at the interactions. Interactions will include things like interspecific interactions. Now, interspecific means between species. International means between nations. And so interspecific means how does one species interact with another? And we can generally classify these into three different things. There could be a plus-plus arrangement, and this means that both of the species involved gain some kind of benefit out of this. This is also called mutualism. And then we have, very common, a plus-minus relationship, whereby in the interaction one organism gains and the other organism is somehow getting a disadvantage. Classical cases in this are predator-prey interaction. Well, the predator species gains, the prey species loses its life, so that's a classical plus-minus interaction. But there are also others, things like parasitism or pathogens. So when it comes to things like bacteria in us, on us, when it comes to different kinds of internal parasites, those would tend to have a negative effect on you, but they would gain from the interaction. And then there's also the minus-minus interaction. That's called competition. And competition really isn't good for either of the organisms involved, because both have to expend energy on interacting with each other, and that energy is not used for good. It's used to basically just keep up with somebody. So competition for space, competition for nutrients is going to be detrimentary to both. Now, as a consequence of this, there are a variety of adaptations that organisms develop to improve in these interactions, to improve their own standing in the interaction. And so you find, for example, when you come to predator-prey interactions, or let's call them predator-prey adaptations, a variety of things that the two will do so that they can improve in their relationship with the other. So when you're looking at prey items, so what can they do? They can hide better, so hiding would be one. They can escape better, so hiding, escaping. They can produce toxins, they have spines, and there's a variety of other things that they can come up with. And in response, and sometimes as part of the same interactions, you'll find that predators do the same kind of thing. Now, they may have very acute vision, acute senses in general, but particularly vision. You find that they have an arsenal of tools to subdue, whether that is beaks or claws or teeth, whatever it takes. And they have speed. And so there are a variety of things that predators and prey do. In fact, you'll find that in many cases, as one organism gets better at escaping, the other one, the predator, gets a little bit faster, because only the best ones are actually going to get the result they want. Something really neat about this is called mimicry. There are two types of mimicry. We have Batesian and Müllerian mimicry. In Batesian mimicry, you'll find that a harmful model is mimicked by a harmless mimic. So an organism that really doesn't have the capacity to hurt anybody looks like an organism that does. So in some cases, the classic example that I show in the lecture is the one of the hawk moth larva. It's just a moth and it's a caterpillar, but the caterpillar's butt end looks really, really similar to certain types of snakes, down to the what looks like the scales on the lips of the snake. So it's pretty amazing. Now in Mullerian mimicry, you have both the model and the mimic harmful, potentially harmful. And so this is kind of a similarity, strength through similarity. If you've seen a bee and you got stung by it, then chances are next time you encounter something that looks like a bee, you're going to be a little bit more careful. Yellow jackets, great example. Yellow jackets are a wasp, a type of wasp. It has a characteristic black and yellow, black and yellow, black and yellow striping pattern. And I tend to encounter any kinds of things that are black and yellow, black and yellow, black and yellow, and students that travel with me and they've ever been stung by a yellow jacket or they know about yellow jackets, they are very reluctant to investigate anything that buzzes and has a yellow, black, yellow, black, yellow, black pattern. And rightly so, because in many instances you'll find that similar kinds of wasps in similar places, which are not yellow jackets, still have that kind of pattern on them. And so the pattern of the one ultimately gives protection to some of the others. So that's Mullerian mimicry. We also can talk about competitive exclusion. And that's a principle that was discovered experimentally, where basically you have organisms that are very similar in terms of their needs. If you find them in the same place, then they will be in competition with each other. Think about this. Every day you come here, you have a need for parking. And there are thousands of others who have the same need. That means there's going to be competition. And not everybody is going to find parking in the particular area that you might be looking for. So as a consequence, there is some competitive exclusion going on, which means you're going to be pushed away from your favorite parking spot and you're going to have to park in New Zealand or one of the other faraway places on campus. And this is in essence a competitive exclusion type situation. Now of course, when we look at this in nature, it could be more dramatic. So you find that organisms that have similar ecological niches they will then have one winner and a loser. So you have the same niche that leads to exclusion. By the same token, some of these interactions are unexpected. You have something called keystone predators. And there are some really interesting examples on keystone predators. Keystone predators, even though they eat things, they actually are responsible for the diversity in an environment. So they safeguard diversity. Because if you didn't have them, some other interactions would take over and disturb the environment. Celebrated examples where this was studied was the type of sea star, which was being removed from a plot of rocky shore consistently for a number of decades, actually. And in the area where the sea stars were consistently being removed on a daily basis, mussels took over, and that was it. Whereas in the area where they were not removed, you had a pretty healthy diversity of 15 or so species, whereas in the other place it was really only one or two. So that's one. The second one is the great example of wolves in Yellowstone. The reintroduction of wolves into Yellowstone National Park about a decade ago changed the environment so completely that it enables the return of songbirds, it increased the diversity of small mammals, it increased the diversity of amphibians and reptiles, beavers came back, they built dams. All of these kind of things happened because the wolves affected the change in the grazing patterns of the deer. Now, not that deer are bad, but there were so many of them in so many areas that they actually disturbed the habitat, and this has now been reversed. So there are a lot of interesting examples when it comes to that. You had a question?
It's actually that, and then also like I guess grass along the shoreline was more plentiful, so it stopped the shoreline from expansion as well too.
Yeah, now there are a lot of examples where you just take one little thing out or change one little thing and it has a pretty dramatic cascading effect. Now the last part of this to know are things called trophic levels. Trophic levels. Trophic means feeding ultimately, and there are various levels at which we as humans can feed. To give you a couple of examples, one trophic level is occupied by a group of organisms called producers. And producers include plants and photosynthetic bacteria. So basically anything that can pick up the light from the sun is going to become a producer. And that is the low end of all of our food chains. And we cannot do without them. So this is one of the key things. Plants are the basis for our existence. Then the next level is that of consumers. And so we have several levels. We have primary consumers, secondary consumers, tertiary consumers, and usually quaternary consumers, and that's where it ends. Now, when you eat a plant, you are a primary consumer. When you eat part of a cow, then you're a secondary consumer. The cow is the primary consumer, you eat the cow, that's a secondary consumer. If you get eaten by a lion, then that lion is a tertiary consumer because it's eating something that's already several steps up in the food chain. And so you'll find that in most food chains, you'll get to the fourth level and that's it. There's nothing that eats the top predator. Like there's really not anything that eats killer whales. There isn't really anything that eats hawks. I mean, there's not a single organism that has as its primary prey killer whales or hawks. And so that's important to know. Two more things before I get to you. And so ultimately, that it gets us an idea of what kind of things are possible in food webs and what aren't. And it also allows us to differentiate organisms between things like herbivores, which eat only plant material, carnivores, which eat only other organisms, omnivores, which could eat either and have a very broad diet, and lastly, the tridivores, which eat all the things that other organisms leave left over, and ultimately eat the decaying organisms themselves. Now, Sean.
I was just about to ask about vultures or something like that.
Okay. So that's the summary of chapter 20.